Then he did his PhD from UC Berkeley. He was at the World Bank for 2 years in the 80s. And he then joined UC Berkeley as a professor, where he retired as the Goldman Distinguished Professor. And then he went to direct, he was the director at the Swiss Institute, the Swiss Federal Institute for Forest, Snow, and Landscape Research, where he supervised almost 550 staff scientists for over 5 years. And now he's joined back as a faculty at Zurich, and he's received so many honors throughout his career. He got the AGU Fellow in 2008. He has the Badmouth Medalist from EGU. And in 2016, he was the AGU's Mind Buying Lecturer. And you know, I could go on. The list is endless. And today he's going to be focusing on the hydrology aspect. But that's, again, a very short part of what he's done throughout his career. So without further ado, let's welcome Jim. We're looking forward to it.
All right, our only problem at the moment is that owing to all of the various audio-visual machinations, this thing may or may not actually work. We'll give this a try. So let me begin first of all by thanking the organizers for inviting this talk, and also for thanking all of you for coming today. I'd like to give a particular shout out to John Hart and Bill Dietrich, who were my PhD advisors when I was here at Berkeley. It's a pleasure to be back here up at LBL. I actually have not been on the ground here at LBL since I myself was a graduate student back in the days when dinosaurs walked the earth. And so it's a pleasure to be back. My central thesis today is that we can learn interesting things about how landscapes work by studying their streams and the solutes that those streams carry. So catchments are fundamental units of the landscape. At any point along the stream, we can define the catchment as the area that drains to that point. And by studying the flow and chemistry of the stream, we can learn a lot about what's going on inside these units of the landscape. And I'm going to illustrate this principle with a visit to one of my favorite landscapes, the Sierra Nevada of California, and in particular, the Sage Hen Creek Basin. Now, as we Californians know, the Sierra is dominated by a Mediterranean climate, and Sage Hen gets most of its annual precipitation as winter snowpack. There's almost no rain all summer. And so there's one big hydrologic event every year as the snowpack melts, and then the catchment dries out throughout the summer. In the Sage Hen Basin, we have an array of various instrumentation distributed around the catchment, although most of the data we'll be looking at comes from this instrument cluster in the lower part of the basin. We have sap flow sensors in several riparian trees and a transect of groundwater wells crossing the riparian corridor, and we also measure water level in the stream, as well as weather and various other factors. So in the midsummer, the daily cycle of the solar flux is matched by a nearly synchronous rise and fall in the rate of sap flow in the trees, and the effects of transpiration are reflected in the groundwater level and in the stream stage. And note that because stream flow depends on the storage in the riparian aquifer, and that storage integrates water fluxes through time, there's a 90-degree dynamical phase lag between the sap flow flux and the water levels in the aquifer in the stream. So as you can see in the top panel, the solar flux is almost perfectly anti-correlated with the rate that groundwater is rising and falling, not with the groundwater levels themselves. So the minimum in groundwater and minimum in stream flow is not at noon when the sap flow is the highest, but instead in the evening when the sap flow shuts down. So here's a visualization of this process. In the morning, riparian aquifer storage will begin to decline, and thus the drainage rate in the stream will start to decline when the transpiration rate exceeds the groundwater recharge rate flowing into the valley axis from the surrounding uplands. In the middle of the day, the transpiration rate will be at its maximum, and the riparian water table will be falling rapidly. In the evening, the riparian water table will stop falling when the transpiration rate declines to the point that it is slower than the recharge from the uplands. Then during the night, transpiration fluxes are negligible, but the drainage from the uplands continues as before, thus gradually refilling the riparian aquifer, such that by morning the aquifer reaches its maximum again. And again, since the aquifer feeds the stream, as the aquifer reaches its maximum, the stream flow reaches its maximum. So here we see the pulse of this riparian ecosystem, and we see the tight coupling between the solar fluxes shown in red and the sap flow rates shown in green, and between the sap flow rates and the rate of decline in the groundwater levels, not the groundwater levels themselves, but the rates that they rise and fall. And that's shown in black and on a reversed scale so that you can see how tightly these things are in fact correlated with each other. Okay, now in the spring during snowmelt, we see a broadly similar pattern, but with the phases reversed, because during the daytime, snowmelt raises the water table and thus the stream flow rises, and at night the stream drains the riparian aquifer, and thus stream flow declines. Now during the snowmelt period, we have evapotranspiration and snowmelt underway simultaneously, and they have opposite effects on stream flow. The cycles in the stream, and to some extent also in groundwater, will reflect the competition between these two processes. So as the melt season progresses, we expect to see a weakening snowmelt cycle and a growing transpiration cycle, and the diurnal cycle in the stream will vanish when these two signals cancel each other. So during the snowmelt period, there will be a positive correlation between the solar flux and the rate of change in stream stage, or the riparian aquifer. During the transpiration period, this correlation will be reversed. So we can plot the correlation for each day as an index of the relative dominance of snowmelt and evapotranspiration. And here's what we see when we do this. It's a complicated diagram. Let's walk quickly through it. Up on the top, we see the accumulation and melt of the snowpack at the bottom of the basin, the middle of the basin, and the top of the basin. Here we see these individual daily correlations between rates of change in groundwater in red, stream flow in blue, and the solar flux. So snowmelt dominated is 1, evapotranspiration dominated is -1. And the gray shading back here shows the amplitude of those daily cycles in, again, groundwater and stream flow. So if we look at the groundwater levels locally in our riparian transect, we see that they shift abruptly from a snowmelt-dominated cycle to a transpiration-dominated cycle, and we see that this happens right when the snowpack at that altitude disappears. That same transition will presumably be happening later and later as you go higher and higher up in the basin. The cycle we see in the stream will integrate the signals from the entire upstream catchment. Thus, we see that when the snow melts out at the bottom of the basin, the stream begins a gradual transition toward a transpiration-dominated cycle as the snowpack retreats to higher and higher altitudes. This transition takes about 2 months, and it ends just when the snowpack melts out at the top of the basin. So we see that the diurnal cycles in groundwater reflect the local balance between snowmelt and transpiration, and the same cycles in stream flow integrate those local cycles over the whole drainage network. We see the same transition at a series of gauging stations along the stream, with the seasonal transition from snowmelt-dominated to transpiration-dominated cycles coming later and later as one goes higher and higher in the basin, and thus into catchments that stay snow-dominated for longer. So again, we see that streams spatially integrate signals from their upstream catchments. Or to borrow a phrase from my friend and colleague Kevin Bishop in Sweden, streams are mirrors of the landscape that reflect in their behavior the physical integration in a very literal sense of the processes in the surrounding catchments. Now at Sagehenge Creek and across the Sierra Nevada, stream flow in the summer depends critically on snow that fell in the previous winter because it's a Mediterranean climate and you just don't get significant precipitation during the summer. So what will happen to these streams if Sierra snowpacks shrink as we expect they will in a future climate? One can, of course, approach this question through modeling, and it's been done. But we took a more empirical approach here, comparing the annual snowpack accumulation as measured by snow pillows, like the one shown on the top here, and the low flows in nearby streams the following summer as measured by gauging stations, like the one shown on the bottom here. And the results of this comparison show there's a systematic relationship between the peak winter snowpack and the low flow in the stream the next summer. That relationship is linear, but it's not proportional. Note that for 5 of the 8 streams that we studied, summer low flows will drop to 0 if peak snowpack accumulation in the winter shrinks to half of its historical average. So that means that 0 flow at the gauging station, of course, not 0 flow everywhere under those conditions. There should still be flow somewhere farther downstream, but not here. Okay? Now, if we look at the last roughly 40 years of snowpacks and stream flow at Sagehenge Creek, we see something rather interesting. So if the summer low flows depended only on the size of last winter's snowpack, we would expect the low flows shown here at the bottom of these annual hydrograph fluctuations, we would expect those low flows to bounce up and down from year to year like the snowpacks do. But instead, the summer low flows seem to have some kind of long-term correlation indicating some sort of longer-term memory. So if we plot the low flow runoff as a function of last winter's snowpack, we of course do see a correlation. But now let's highlight the cases where the snowpack 2 winters ago was well below average. And we see that if the snowpack 2 winters ago was small, minimum flows this summer will be low, almost regardless of how big last winter's snowpack was. On the other hand, if the snowpack 2 winters ago was well above normal, this seems to sort of prime the groundwater system and make it rather sensitive to last winter's snowpack. Now, if we plot summer low flows as a function of the snowpack 2 winters ago, we again see that there's a clear correlation. And we see that even the snowpack 3 winters ago has a clear effect. Now, in this part of the Sierra Nevada, the granites of the Sierra Nevada batholith are covered by Miocene volcanics. And as a result, Sagehenge Creek has a groundwater aquifer with a residence time of about a decade or more. So what we're seeing here is that this groundwater aquifer gives the stream a long-term memory of snowmelt inputs 2 and even 3 years ago. And note that this memory is not reset by recent snowmelt, suggesting that the groundwater system is not as simple as a typical bucket in a typical conceptual catchment model. So we see that streams not only integrate signals from throughout their drainage networks, they also integrate back through time and sometimes much farther back than we might have assumed. Now, streams aren't just mirrors of the landscape, they're also features of the landscape. One of the most obvious features of any landscape is its branching network of streams. And here we need to distinguish between 2 different kinds of networks. The geomorphic network of stream channels is a more or less permanent topographic feature of the landscape. On the other hand, the active drainage network, meaning the network of water flowing at the surface, may occupy only a small fraction of the geomorphic channel network, or may extend beyond it. This active drainage network dynamically extends and retracts and connects and disconnects in response to hydrological conditions. Sarah Godsey undertook to measure this network extension and retraction as part of her dissertation here at Berkeley. And to do this, she walked the entire drainage networks of 4 experimental watersheds in the Sierra Nevada and the California Coast Range under both wet and dry conditions. So let's look at Sage Hen Creek as an example. Under wet conditions, Sage Hen Creek is a 4th order network and has about 35 kilometers of channel. But under dry conditions, Sage Hen Creek is only a 2nd order network with only 15 kilometers of channels. So is Sage Hen Creek a 4th order basin or a 2nd order basin? It depends when you ask that question. Notice also that at low flows, a lot of the flowing network has become disconnected from the outlet. So the aquatic habitat in the stream has not only shrunk, it has also become fragmented. And it's also worth considering the kind of field work that's required to do this. Mapping 35 kilometers of stream channels requires walking 70 kilometers because you've got to walk up and down every link in the network. And this is mostly walking overland through rough, brushy terrain, and there are few roads and few trails in the Sage Hen Basin. And Sarah did this 4 times, and in 4 other basins, some of them even rougher than Sage Hen. So although Sarah is a woman of fairly small stature, she's an awfully tough lady. You don't want to meet her in a dark alley. Now, across the basins of this particular study, we found broadly consistent power law scaling between the drainage density and the stream discharge, with a scaling exponent of about 0.3 in this case. Now, the slope of this power law relationship, it describes how dynamic a stream network is, how much it extends and retracts for a given change in catchment wetness and thus stream discharge. What is that behavior trying to tell us? So the existence of active surface drainage is direct evidence that the water flowing from the upstream catchment is more than we can accommodate as subsurface flow down the valley axis. So, for example, we know that in the valley on the left, the down valley transmissivity of the riparian aquifer is too low to carry all the flow from the surrounding catchment. So the flow is forced to the surface. Whereas in the catchment on the right, it isn't forced to the surface, at least under these conditions. So the extension and retraction of the stream network is dynamically mapping out the balance between subsurface transmissivity and the amount of flow that's being delivered from upstream. Jeff Prancevic and I have recently shown that we may be able to estimate how dynamic stream networks are just by looking at topography. So where flow lines converge on the landscape, drainage area accumulates rapidly in the downstream direction. So drainage networks in strongly convergent topography should be relatively stable because as we go downstream, discharge rapidly becomes more than enough to support surface flow. Similarly, where valley profiles are strongly curved, the rapid decrease in slope and thus the rapid decrease in subsurface flow velocity should force groundwater to the surface. So where this curvature is sharp, flowing channel heads should be relatively fixed and networks should not be particularly dynamic. Third, wherever the valley cross sections are sharply curved, valleys will be narrow and the compressive stress in the subsurface will be relatively strong, tending to reduce the subsurface transmissivity. So where cross-valley curvature increases rapidly in the downstream direction, flowing channel heads should be relatively fixed in place and networks should not be particularly dynamic. So the 3 mechanisms that we've just described all follow some kind of scaling relationships. And we can combine these scaling relationships to predict the scaling exponent for the network length itself. This is not an empirical construct. The form of the relationship is dictated by physics. And as you can see, it does a reasonably good job of determining which networks will be highly dynamic out at the end of that line and which networks will be relatively stable. The plot represents the entire global data set of measurements that can be used to test this theory. And we clearly need more of those, but they're not easy measurements to make. Note also that whenever there's surface flow on the landscape, there may also be channel incision. And channel incision will tend to reduce channel slopes, increase cross-valley curvature, and increase flow convergence. And these same three characteristics will all tend to make networks less dynamic. So there may be a long-term geomorphic feedback process that stabilizes stream networks. That's consistent with the observation that the most dynamic networks in this data set are found in catchments that retain some evidence of glaciation. Those are shown as the squares in this figure. And networks that are more stable are where any glacial history has been erased by fluvial incision. Those are the circles in this figure. So this suggests that topography and long-term patterns of erosion may determine much of the dynamic response of flowing stream networks to catchment wetting and drying. So in summary, most of us who have been out in the field anyway, understand that headwater stream networks dynamically extend and retract and connect and disconnect. But there's been surprisingly little work done to study this. I'll give a shout out, however, to the work of Bill Dietrich and Sky Lovell in the Eel River Critical Zone Observatory, which also involves some truly epic field work. More broadly, this phenomenon matters, not only for aquatic habitat, but also for models. If the length of the drainage network shrinks by a factor of 2, the average distance that a raindrop has to travel underground to reach the nearest channel also changes by a factor of 2. And that fact is widely ignored in hydrologic models. Now, so far in this talk, we've looked at how landscapes shape the hydrologic system. But this can, of course, also go the other way. That is, hydrological processes may also shape the evolution of the landscape itself. And I'd like to look in particular at stream junction angles and how they vary across the landscape. Hans-Jörg Seibold took the best current digital database of stream networks in the US. This is called NHD+. And he calculated the junction angles at nearly 1 million stream junctions across the country. And he then compared these junction angles to various climate and terrain variables. And what emerged was a clear relationship between climatic aridity and the mean junction angle. Not individual junction angles, but averages over thousands and thousands of junctions. On the left, you see the map of mean junction angles, and you see that it broadly corresponds to the map of climatic aridity. Now, obviously, the west is not just drier, it's also steeper than the east. And there are various other differences. But even after we correct for every factor that we have data for, including topographic roughness, the dependence on aridity still persists. And when we average over bins of aridity, we see that the most arid landscapes have mean junction angles between 45 and 50 degrees, and the most humid landscapes have mean junction angles around 70 degrees. At the global scale, the most detailed digital networks are in what's called the Hydrosheds data set, and those are at substantially lower resolution than the US data. But in those data too, we see a broad correlation between climatic aridity and stream junction angles, but with more noise than we saw in the continental US. Now we can also find channel networks, or things that look an awful lot like channel networks, on Mars. And these channels have not been active for probably 3 billion years. But can we learn anything about the conditions that might have made them? And except for the lucky few who have got to go to Mars virtually by rovers, what we're going to have for the foreseeable future is images like this to work from. So there have been 2 major efforts to map the valley networks on Mars using different data sources and different techniques. And if we overlay the global distributions of network angles from Earth, we see that the junction angles on Mars are narrower than those on Earth, and even narrower than in Earth's arid regions. Now, of course, right, Mars has a weaker gravitational field, but you can show by simple physics that the weaker gravitational field will only affect the speed and not the direction of flow and sediment transport. So it shouldn't affect the planform geometry of channel networks. Now, what I'm about to say is really speculative, probably even by the standards of planetary science. But you can interpret these distributions as implying that the climate that made these networks had more in common with Earth's hyper-arid regions than Earth's humid regions. And if we look at the visual pattern of some of these networks, and in particular, if you look at the low-order channels that are hard to see on this slide, you can convince yourself that Earth's arid region networks are indeed a much better match for the Martian networks. Okay, but to come back home and to come back to some practical matters. Now, I probably don't need to convince anybody in this room that floods are important to study, to model, and also to manage. But we often study and manage floods on a basin-by-basin basis without recognizing that flood risks of different rivers are often strongly interconnected. And understanding how floods are synchronized will help in understanding how water moves through landscapes and over what scales. The synchronization of river floods also amplifies their impacts and their financial risks, because when floods on different rivers tend to come at the same time, so do their impacts. And the resources to deal with them in terms of emergency response must also be available at the same time. You can't send the same emergency response team to 5 different rivers at once. So this raises the question over what scales are flood risks synchronized. So here we see the dates of annual maximum flows over a database of 4,000 stations throughout Europe. Now, unfortunately, this database only has information on when these flows occurred and not how big they were. Nonetheless, just from the timing of annual maximum flows, we can begin to visualize something about how clustered versus dispersed these events are. So we can define, since we're making up the terminology, we can define these things any way we want. We can define a flood synchrony scale as the radius around a given station where at least half of the other gauges also flood within plus or minus 7 days. You can define it many other ways. This is the way we've decided to define it for purposes of illustration. So here is, for example, the Jaworzno River in Poland, and this is the circle around that point where on that day, its highest flow of 1997, more than half the rivers were also flooding in plus or minus 7 days. That happens to be otherwise known as the Great Central European Flood of 1997. Over here in Spain on the same day, that river also had its annual maximum flood, but the other rivers nearby were not particularly involved. So if you aggregate these data over all of Europe and over a 50-year record, you can define the average scale of annual flood synchrony, and you can see that in general, flooding is synchronized over scales of hundreds of kilometers across much of Europe. But it's more localized in the mountain regions of the Alps, the Pyrenees, and the Carpathians. We also see, if we look year by year by year, that floods have become more synchronized over larger and larger areas over the past 5 decades. Now, at present, there's no explanation for that phenomenon, but it's clearly there in the data. So, to conclude this little section, we see that annual floods are synchronized over scales of hundreds of kilometers. Note that this is areas of tens of thousands of square kilometers, so roughly Switzerland-sized pieces of landscape. And we see that this flood synchrony scale has been growing over the last 5 decades. I haven't shown it here, but the data also show that periods with above average flood synchrony also tend to follow one another. That is, if you have higher flood synchrony in one year, you probably have higher flood synchrony in the next year as well. And the spatial scale of flood synchrony is much smaller than the spatial scale at which precipitation itself is synchronized. So this isn't driven by anything as simple as widespread precipitation means widespread flooding. Okay, so I'd like to talk now about not the volume of water flowing, but instead what's in that water. And solutes can, of course, be interesting either because they're contaminants or they're nutrients and therefore interesting in their own right, but they can also be interesting because they contain passive tracers or reactive tracers that tell us where water has been and how long it's taken to move through the landscape. And of course, one of the best tracers are the isotopes of hydrogen and oxygen themselves, because those are embedded in the water molecule. They inherently follow the water. As an illustration of this, we're going to use isotopes of water in sap flow in trees to try to determine when the water that's in those trees fell as precipitation. Now in Switzerland, as in virtually everywhere that's far enough from an ocean, there's a clear seasonal cycle in the average isotopic value of both deuterium and oxygen-18 in precipitation. So summer is isotopically heavier than winter. Summer precipitation is isotopically heavier than winter precipitation. And so we can use the isotope ratio as an index for when that water that we might measure in a tree fell as rain. So here's the sampling protocol. And I will say in advance, we didn't do this. This was done by the Institute of Applied Plant Biology up in Basel. But I totally want this job, because the way you do this sampling is you get a field technician, you put him in a harness, you attach him by a cable to a helicopter, and then you fly him around your field site, and he uses a pair of clippers to clip off branches from the crown of the tree. And then you have minions who go scurrying around on the ground and gather these things up and bag them and so on, so that we don't lose anything to evaporation. And we did this, or our colleagues did this, for nearly 1,000 trees at over 100 field sites around Switzerland, using funds from the Federal Office of the Environment. And here's what you get from an isotopic analysis of that sap flow. So here we have the isotopic signature of summer precipitation. Here we have the isotopic signature of winter precipitation. And here, coded by species, we have the isotopic values observed in the xylem water at the crowns of those trees in August. Okay, so we're looking at the water that's in the tree in August, and we are seeing very clearly that except for spruce trees at high altitudes, that water looks a lot like winter precipitation. Now that observation has a number of important implications. First of all, paleoclimatologists use isotopes in tree rings to try to infer the isotopic values and therefore climatic variables surrounding growing season precipitation. But if the xylem that's present in the tree in the growing season fell as winter precipitation, then you're actually measuring a winter signal, not a summer signal. This also has hydrologic implications, because it implies that summer rainfall does not substantially refill the root zone water storage, and that the turnover of water storage in the root zone must be minimal throughout most of the summer, either because summer precipitation never gets there because it evaporates, or because summer precipitation bypasses winter storage or root zone storage and simply goes to groundwater. So I'd like to now talk about how we can use isotopic tracers to understand how long water stays in the landscape and where it moves through the landscape at several different scales of both time and space. And a clever young wizard of this particular kind of magic is Scott Jascheko, who is now at UC Santa Barbara. And I'd like to briefly mention some work that we've done with him and with Jana from Freiberg at ETH Zurich. So we can use the seasonal cycles in precipitation isotopes also as reflected in streamflow to figure out, roughly speaking, how much of history is averaged together in that stream. So you can see intuitively here that this particular stream in the Alps must be integrating across at least roughly a year of previous stream flow so that the ups and downs balance each other out and the stream flow isotopic signature doesn't vary a lot. Conversely, this stream in the foothills of the Alps has a much larger amplitude and thus must have a stronger contribution of recent precipitation to its stream flow. Now, I showed a few years ago that you can take the ratio of the amplitude in stream flow and the amplitude in precipitation and calculate what's called a young water fraction, which is the fraction of water in that stream that's less than approximately 2 or 3 months old on average. And that's the way you get that time scale is to observe that beyond 2 or 3 months, the ups and the downs start to cancel each other out, okay? So you're looking at, so that ratio tells you what fraction of your water is not canceling out other water and therefore must be 2 or 3 months old or younger. Okay, so I developed that method so we could use it on hundreds of rivers around the world. And we've done this using 2 international databases, the Global Network of Isotopes in Rivers and the Global Network of Isotopes in Precipitation, both of which are compiled by the IAEA in Vienna. And when we do this for every river in the world for which there are data, and those are very strongly clustered, as you can see, we see that almost all of our rivers have young water fractions of less than 40%, with an average somewhere around 20 or 25%. And that pattern is consistent for small experimental catchments and some of the largest rivers on Earth. It's consistent across places where the water table is within a meter of the surface and places where it's hundreds of meters deep. And it's consistent across aquifer permeabilities that vary by more than 7 orders of magnitude. But we do see an intriguing pattern in North America and Europe, the 2 regions where we have particularly dense data. Look for the red dots. The red dots indicate rivers that have very little young water. Where are those red dots? Well, there are a few in these major rivers of Sweden. Those rivers drain big reservoirs. So, of course, they have very little young water in the outlets. But otherwise, most of the red dots are in the Rockies and the Alps. Think about that a minute. It indicates that rivers draining mountainous regions have smaller fractions of young water, not bigger. And that may seem counterintuitive because you might assume that steep landscapes should shed water faster. Nonetheless, the correlation with topographic slope, although it's scattered, is clearly there. And although you might intuitively expect that steep landscapes should have more near-surface flow and younger stream waters, our data suggests the opposite, and we actually think it makes physical sense. Steep landscapes will create geotechnical stresses that tend to open fractures in the subsurface, promoting deeper infiltration and longer, not shorter, transit times. And we think we're seeing data here indicating that influence. And by the way, we have filtered out from this data set the effects of varying amounts of snowpack accumulation in the mountains, which of course would be an obvious explanation for what we see. Okay, so that's stable isotopes. Now, you can also use a number of other interesting isotopes. So Scott Gischecko has shown that if you take the historical curve of tritium and rainfall, those are the gray dots in this graph, and you see the huge hydrogen bomb peak there back when some of us old guys in the room were in grade school. And note that's a log scale, so that peak is really, really big. So if you correct each of those samples for the decay that it would undergo as it ages to the present day, and those are the black dots, you'll see that any rain that fell before the bomb pulse has a present day tritium concentration of less than 1 tritium unit, which makes it unmeasurable by conventional techniques. Conversely, almost any sample that fell after the bomb pulse has a present day concentration around 10 tritium units. So you can use these two approximate end members to quantify the fractions of young and old water in mixed samples, where now young and old mean basically younger and older than people like me and Bill Dietrich and John Hart, for example, okay? And you can do something similar with carbon-14, except then you're measuring the fraction of water that, roughly speaking, is younger and older than the Holocene. So Scott Gischecko has compiled a database of isotope measurements in about 6,000 wells around the world. And the tritium in those wells shows that most groundwater below about 70 meters depth is over 50 years old. And here we see Scott's carbon-14 data grouped into 64 global aquifers. And the red bars indicate that below about 200 meters depth, 200 meters here, below about 200 meters depth, depending on the aquifer, most of the water is pre-Holocene. Now, that water accounts for the great majority of all the groundwater on Earth. So most of the groundwater on Earth is predominantly pre-Holocene in age. Now this creates a real puzzle, right? If aquifers are generally really old or downright ancient, then the rivers that drain those aquifers are much, much younger, then how does that work, right? If a quarter of the flow in those rivers is less than about 2 or 3 months old, how can it be that the aquifers are, you know, tritium says mostly more than 50 years old, carbon-14 says mostly more than several thousand years old? How does that work? So the key is to realize that that is not a paradox, or it's only a paradox if you think that aquifers and catchments are well-mixed tanks that should have the same age everywhere, when in fact they're highly heterogeneous. So if an aquifer is heterogeneous, and that is a statement you can make about every aquifer, it's heterogeneous, then the highest conductivity parts of the aquifer will supply most of the stream flow because those high conductivity parts flow the fastest. And that water will be the youngest because those parts flow the fastest. And conversely, the low conductivity parts of the aquifer will have the oldest water, but that water will be old precisely because it isn't being delivered to streams. So it doesn't make up a significant part of stream flow. And as obvious as that observation is, it's apparently non-obvious enough that you can get it published in GRL in 2017. So here's another interesting result from this work. People often assume that ancient aquifers are immune to modern day contamination. But if aquifers are heterogeneous, and aquifers are, then those aquifers can contain waters with very wide distribution of ages. So if we look at our groundwater samples that are significantly depleted in carbon-14, which means that they must be thousands and thousands of years old, we see that fully half of those samples have detectable amounts of tritium, which means that they can't be older than several decades. So those really old aquifers must have a component of water that's only decades old, not centuries or millennia. And that means that they could very well be vulnerable to modern day contaminants. Now let's look at a much shorter time scale. Let's look at the response of individual streams to individual storms. And let's consider the standard model of storm runoff generation, which was taught for decades and is probably still taught some places today. In the standard model, the storm flow peak of the hydrograph is assumed to be mostly new water, that is recent rainfall, that reaches the stream rapidly by overland flow or macropore flow. And that storm flow was assumed to be superimposed on a slowly varying base of old water from previous storms, which reached the stream slowly via groundwater flow paths. And it's easy to see where this standard model would come from. I mean, after all, runoff responds really quickly to rainfall, and it seems logical that storm flow peaks should be recent rainfall. And that's indeed what happens in some arid landscapes and in and in urban catchments. But in most humid landscapes, we know that this standard model is just plain wrong. And we know it's wrong because if the storm peaks were mostly new water, their tracers should resemble the new water, but they don't. Instead, the tracer concentrations are much less variable than those in the precipitation, indicating that what we see in the stream, even during storm peaks, must be an average of water from many previous rain events. Okay, but that just creates another puzzle. And that puzzle is, how does this physically work? How do landscapes store water for weeks or months and then mobilize it in a matter of minutes as soon as rain falls? Now, there have been a number of theoretical mechanisms proposed under names like piston flow or transmissivity feedback or kinematic waves, but the devil's in the details and there's a lot of work to be done here. So although this question remains open, I'm highlighting it here to illustrate how these sorts of tracers have been driving our field forward. One way to think about this problem is that when rainfall hits the ground, it does two different things. First, rainfall changes the hydraulic potentials at the ground surface, and those potentials propagate through the landscape with a given wave speed or celerity. Secondly, rainfall adds water to the landscape, and this water then flows through the landscape with a given velocity. We know that the velocity of the water movement must be much slower than the celerity of the hydrologic potentials. That's the only way storm flow in streams can be only a small fraction new water. But until recently, we haven't had good ways to measure either of these landscape responses to rainfall. We can illustrate this with a simple nonlinear two-bucket hydrologic model, and we can add a pulse of rain and tracer, and we can see that the discharge pulse may disappear in a couple of days, but the tracer may persist in groundwater and the stream for long, long periods of time. And the question is, can we measure those characteristic patterns of response in the real world from data? Well, I wouldn't be presenting this if I didn't think we could, right? I'm going to show you data from the Alp catchment in the foothills of the Alps, and in particular the Erlenbach research catchment, which is about 2% of the larger basin itself. And we're going to look here because the Erlenbach exhibits a truly violent response to precipitation. It can go from roughly this state to roughly that state in about an hour. So the classic way to estimate the fraction of new water in stream flow is by using isotope hydrograph separation, which requires that we sample intensively during individual storm events. And it also requires that your two end members, those being precipitation and pre-event base flow, are isotopically distinct from one another. Now here's an example of where this doesn't work, because the isotopic signatures of the rainfall and the old water are not meaningfully different from one another. When those two end members overlap, you'll be dividing by 0 or nearly 0 in the mixing equations, and that can lead to crazy results like new water contributions that are negative or more than 100% and so forth. And normally when that happens, a hydrologist will simply ignore that event and go look for another one where the mixing equations work. And you can call that cherry picking, of course. But thinking about that problem, I realized that if you don't want to look at individual events, but instead you want to characterize behavior over an ensemble of events, you can transform the end member mixing equation into a simple linear regression equation. In other words, we simply ask, how are fluctuations in precipitation and streamflow tracers correlated with one another? And what's the slope of that relationship, as shown here on the bottom? One advantage of this method is that now we're multiplying rather than dividing. So the same points that would lead to a divide by 0 problem in conventional hydrograph separation will instead lead to a value of 0 on the x-axis here. And that means that the same points that would blow up your solution in conventional hydrograph separation instead become points with no leverage on the solution in this analysis. Now, when we test these methods with model-generated benchmark data, we get estimates of the average new water fraction. New in this case means new since you took your last stream sample, okay? New water fractions that agree almost exactly with the true average as determined from age tracking within the model. I'm not saying this is an accurate model of how catchments actually work. I'm just saying it's a simple enough model I can use it to test this data analysis technique to verify whether that works or not. So it turns out we can not only estimate the fraction of stream water that's composed of recent rainfall, we can also estimate the fraction of rainfall that reaches the stream quickly. And those are not the same number, as it turns out. And we can do this analysis on hourly timescales or daily timescales or weekly timescales, whatever timescale we have data for. Now you can even generalize this approach and derive a multiple regression method that gives the distribution of water ages for a range of lag times. Now, this isn't conventional multiple regression because precipitation is intermittent, so you don't have precipitation samples at every lag time relative to every stream sample. So you need to use some unconventional methods to make this work. And the math gets really, really ugly here. And if you want to read it, if you want to see it, read the paper. I won't show it here. Instead, I'll show my 2 research assistants who helped me check all the equations. That's a lot more pleasant to look at than the equations themselves. Okay, onward. We can also do the same thing with water flux data. So we can get the impulse response of the system, the unit hydrograph, if you want to think of it that way, which is tracking the celerity of the hydrologic potentials through the system. And we can verify this analysis using perturbation experiments in the benchmark model, where we add a little extra tick of precipitation at each point in time, and we track how that extra water decays. Okay, now back to the field data, and we're looking at 2 different spatial scales, less than 1 square kilometer and nearly 50 square kilometers, and we're looking at 2 different time scales. We're looking at daily water fluxes and isotopes, and we're looking at hourly or sub-hourly rainfall and stream flow. So we have about 4 years of daily measurements of isotopes in precipitation and stream flow at several sites in this basin. And this is just a short subsample of that data set. So if you do the analysis that I've just described, here's what you get. So these here are the hydrologic response functions. This says, in other words, that when you have 20 millimeters per day of antecedent discharge, indicating that that's a certain level of antecedent wetness in your catchment, then if you get 1 millimeter of rain today, you'll get about 0.6 millimeters of runoff today. But only about 0.05 millimeters of that runoff will be the same precipitation that fell today. So this is the transit time distribution for the water moving through the catchment. This is the same thing on an expanded scale so you can see it. It expresses the proportional response of the streamflow volume flux itself. And you can see the sensitivity of both of those to antecedent wetness. Now, intriguingly, this is essentially the same plot, either at this very small scale or at the much larger scale. I don't know why that's true, but it is. And you can see here very clearly that this hydraulic response is much stronger and much more sensitive to wetness than the velocity of transport of the water through the catchment itself. Although that also exhibits a clear sensitivity to wetness. Okay, so we can also look at the transit time distributions, the distribution of lag times that we see in the stream. And we can do this again, both for the hydraulic potentials and for the tracers that track the movement of water itself. So here's the plot for the hydraulic potentials here at the scale of the whole large basin. And here is the transit time distribution of the water itself. Here's the same thing for the Erlenbach subcatchment and its transit time distribution. So note the very sharp short-term peak in the propagation of the solarities and the very damped response in the velocities. Okay. Now, that was daily data. If you now look at the coupling between precipitation and stream flow at a time scale of minutes, and the dark line here is 10-minute data, you see that that big peak is actually a rise and fall, and that it reaches its peak within less than an hour, and it does so at essentially the same time scale, whether you're looking at the small subcatchment or the main catchment itself. So storm flow peaks occur within about an hour, and they only last about 4 to 6 hours, which means we shouldn't be looking at this with annual data now, or sorry, with daily data now, should we? So we installed an isotope analyzer in the field, as well as an ion chromatograph to analyze for chemistry and a bunch of other fun toys, and set this up so that it would automatically drink from the stream every 30 minutes or so, except when it rained, and then it would drink from the rain collector, and it would run that analysis here, record the data, and so forth. Because you don't want to be putting that many samples into individual bottles in an autosample. This is the view you get of isotopic and chemical dynamics if you're willing to make those measurements at that kind of resolution in the field. So you see, for example, this is the springtime, and we have intermittent snow melt, and you can see that in the stream flow itself. You see the dilution in the electrical conductivity. You see bumps up and down in sulfate concentrations, just as one example. And you see the incredible variability of isotopes in precipitation and the incredible stability of isotopes in stream water. Although if you take that gray line and you blow it up, you do get those kinds of dynamics. So there is real behavior there. Let's contrast that to the kind of view that we've had before. So at this particular site, we have about 10 years of samples every 2 weeks. And this is what a few years of that record looks like. And then from our recent daily sampling, we have samples every day, of course. That's what that record looks like. Here's what that looks like over timescales of 5 weeks. And here's what the detailed isotopic record is showing us is going on over those kinds of timescales. Note in particular the remarkable variability in isotopic values in precipitation, even during individual storm events. So here is one storm event where the deuterium ratio in precipitation varies by more than 100 per mil. And 100 per mil is, roughly speaking, the entire range of annual variability we have at this site. And it's all happening due to convection internally within that one event, or due to evaporative fractionation of the light rain at the beginning and end of the event, and we're not sure which of those two is responsible. So this is like being an astronomer with really bad eyesight and someone just gave you a telescope. Right? We're suddenly seeing our system in unprecedented detail. And here's what you get if you do that kind of lag time analysis that I just described. You're only the second group to see this stuff. If you do this with those samples that are taken at roughly hourly resolution. So here again is the hydraulic response function for this small subcatchment. And here's the transit time distribution in the stream flow. So we're not getting the damped response in the isotopes because somehow they all snuck out of the system during the rain event. We can verify that this is not happening over those short timescales. And again, if we look at timescales of days, we see this pattern here. And all of this behavior up to right there is all embedded in that first data point in both of those axes. Okay, so I want to conclude by thanking the small army of people who were involved in creating those data. And I'd like to summarize simply by reiterating some of the main points here. That we've seen that diurnal cycles in streamflow and groundwater tell us interesting things about how landscapes function. We've seen that stream networks are highly dynamic. That's telling us also something about how landscapes work. We've seen that valley junctions vary systematically with climate. That's also trying to tell us something about how landscapes work. We've seen that floods are synchronized. We've seen that trees use winter precipitation even in midsummer. We've seen that storm flow is mostly old water, that steeper landscapes have more of that older stream flow, that aquifers are ancient compared to the streams that drain from them, that makes sense if you understand aquifer heterogeneity. And finally, we've seen that hydraulic potentials propagate a lot faster than the water itself moves through the landscape, and that both the velocity of water movement and the celerity with which those potential waves propagate can be quantified directly from data. So thank you all for your kind attention. I've probably tortured you enough today, and you've been very kind. Thank you.
That was a great talk.
Thank you.
Questions?
John.
Yeah. When we look at long-term trends like in the synchronization of floods, what role, if any, do you think the increase in the built environment to manage landscape has played in that creating some trend?
I mean, we've certainly wondered about that ourselves. We don't have a good answer. The most obvious thing to do there would be to try to separate out places where there has been dramatic land use change and where it's been less pronounced. We haven't done that yet, but it would be an interesting thing to look at. But I will say I would expect that to influence the magnitude of flood peaks more than how floods are synchronized in adjacent basins. But what do I know? I need to stay open to being surprised because virtually everything I've reported here today started out as a surprise.
I was just curious about heterogeneity of the groundwater.
So I do not know if that's been explored theoretically. I mean, there's an entire field called stochastic subsurface hydrology, right? Which is generally about looking at heterogeneity at very small scales and trying to aggregate that so you understand behavior at sort of borehole to borehole scale or something like that. How this works at the scale of landscapes, I don't think has been explored, but I'm happy to be corrected about that. Most of the groundwater people I talk to basically say that these results are simply impossible, that what we must be seeing, and we have to admit that this is a possibility, what we must be seeing is recent rainfall that's gone down the fractured rock adjacent to our well. Remember, these are borehole data. You don't get borehole data unless you have boreholes. And boreholes do a lot of destruction on their way into the ground, right? You've created a local zone of fracturing, which you try to isolate, you know, packing things with bentonite and so on, but it's not perfect, right? So I would love to be able to find a groundwater sample that didn't require a borehole. And I think we actually have a strategy for that. Because I live and work in Switzerland, and the Swiss love to make tunnels, right? And a tunnel is basically a borehole that's coming in from below. Right? So what I want to do the next time they build one of these gigantic tunnels is I want to walk behind the tunneling machine. And I want to sample the water that's seeping out of the walls, you know, fresh, right behind the borehole, the boring machine. And if that water has a mixture of depleted carbon-14, but the presence of tritium, right? If that water has it, then we know it's in the aquifer itself. It's not an artifact of installing a well. Yeah.
My question was sort of related. Show that the streams move in different order based on right now. Do you expect the same? Do you expect the same process to occur in subsurface fraction of that subsurface road network would also change?
So the question was, would we expect essentially network extension and retraction in the subsurface? And I would say, obviously, we expect the flow network in the subsurface to change as we add and remove water, at least in the transitional zone between the saturated and unsaturated groundwater. Within the saturated zone, I think it's relatively hard to argue for a big influence. But of course, any hydrologic system where you have strong gradients in permeability with depth, for example, those, or strong non-linearities, those systems will tend to perch right at the nonlinear transition between a system that won't drain and a system that dumps everything, right? So we expect the system to sort of, as it fills up, to fill up right to that point to where it becomes highly sensitive. So this may be something worth considering. So that's an intriguing suggestion that there might be some, you know, branching angle in the subsurface, although I would expect that those branching angles would be set by the basics of how fractures branch, for example, in heterogeneous brittle materials like rocks, rather than through the sort of interplay of flow and sediment transport that we see at the surface of the Earth. Maggie.
A question about the synchronization of floods and if not. I mean, I just wanted you to say a little bit more. Is that 60 or type of precipitation pattern that you have just very much of that runoff synchrony, flood synchrony, or is it any? Just say a little bit more.
Okay, I mean, at some level, yes. I mean, at some level, you can't have synchronized floods unless you have synchronized inputs, right? So you can't have flood synchrony without precipitation synchrony. What we observe, however, is that if you apply the same synchrony scale definition to precipitation, rather than to floods and rivers. And so now we're looking at annual maximum precipitation rather than annual maximum flow. We see that the spatial scale of annual maximum precipitation synchrony is much larger than the spatial scale of flood synchrony. And we see that it doesn't vary across the landscape the same way that flood synchrony does. So floods are more synchronized, or floods are synchronized over smaller spatial scales in the mountain regions of Europe anyway. We don't see the same pronounced change in the spatial scale of the synchrony in precipitation. So if you do the same map, you see basically a broad smear across all of Europe. You don't see spatial variation. Now, I will say, we're obviously repeating this analysis in North America, where we not only know the day of the annual maximum flow, we actually know what that flow was, right? And so we can do a lot more analysis because we know the full flow distribution. But yeah, exactly. Well, obviously, so there are a couple of things embedded in that, right? One is that, of course, you would expect upstream and downstream gauges on the same river to hit their maxima roughly at the same time in a given year, right? And there's a few percent of our data set that's doing that, and we can take them out and it doesn't change the results in a basic way. So what we're mostly seeing is synchronous floods in adjacent basins, not in nested basins.
I'm curious about the network not always being connected.
Yep.
And I'm guessing more rain, the more connected they become. Something about those basins.
So the field evidence is that this connection and disconnection happens where locally you have higher permeability in the subsurface. So upstream and downstream, you can't accommodate all the flow as groundwater, but in between you can. And as a sort of trivial example of this, one of our field sites is Casper Creek in the Coast Range here. And there are many points along Casper Creek where the adjacent hill slopes and small basins, small tributary basins, have dumped loads of coarse material right in the valley axis, right? So the stream will disappear under a pile of debris, basically, and reemerge on the other side. And where those piles of debris are small enough that, say, at high flow, the stream will bridge over them, but at low flow, it will tunnel through them. Then you get this connection and disconnection phenomenon. You also see this in other places you would expect it, like where the longitudinal profile of the stream goes from flat to steep and back to flat again, right? So in that steep reach, the gradient in the groundwater is steeper, the potential flow velocity in the subsurface is higher, and you can locally disconnect there at low flows, for example. Others of these are presumably related to local fracture connections in the bedrock. That's, of course, speculative. I mean, we know that in general, what's under our feet is pervasively fractured. And so it's always an easy thing to blame any phenomenon that you can't explain at the surface on, some unobservable combination or connection in fractures in the subsurface. But presumably that's responsible for some of it. Bill?
I think of how you think about how the signal that arrives at the surface then gets out. Unsurprisingly, I think I will ask a question about the mixing process. That's it.
Yeah.
And the beta stuff, are, let's say, kills everything. But all the water that's in there is deep. And so I wonder about how the question of, you here you get a there, but is it related? That is, how much of that signal is processed in the same processes the water found in the system, such that your interpretation is effective about what's old and young. And it sort of doesn't. We have at our site, water but it doesn't have the rainfall signal. And it could be interpreted as old water being pushed out, but it's not.
Well, so if you're saying it's not old water, how does it get rid of its isotopic signature on the way through?
It mixes with the water step. So, for example.
Yeah. Okay. So it's exchanging old water and new water, and the water that's coming out is predominantly old. Yes.
But okay, that's fine. So this happens in the datas.
Sure.
And so in our case, we get a tenth of the amount of rainfall get is enough to bring the stabilized temperature up to the average rainfall.
Yep.
So any water that passes there can mix and come out, and the signal will look like old water, but the water that's in there could be in there for a short period of time, but it's mixed back. So there's yes, it's mixing with water there, but it's not years old or months old. It's I feel like there's a mixing process that can change the signal that doesn't imply a debate. You know what I'm saying? Because it doesn't take very much of the cumulative rainfall in our given narrow range,
Right.
to get a down signal. So where this goes to is you're coming about the mountains, steeper landscapes have old water.
Yeah.
Could it be that steeper landscapes have this mixing process that damps out the signal? And it's not so much just older, it's just the water can't get out, but how it mix storage.
Okay, but so
You know what I'm saying?
yeah, I do see what you're saying. I mean, it's important. I think I see what you're saying. It's important to be careful about how you define things like old and new, and to use a fairly strict definition of what that is. So depending on how you're doing the analysis, I've given you examples where we talk about young and old, and that's a 2 to 3 month time scale, and that's based on the seasonal cycle in isotopes, right? And then I said, there's another way to do an analysis where we're talking about, 50-year water and 5,000-year water, and another way to do the analysis where old just means old since the last time we sampled the stream, right? And all of those definitions work if you apply them with the tools that we've been talking about. And the only way they would not work in some rigorous sense is if you somehow believe that the water can somehow be disconnected from the isotopes that are in the water. And there's no physical mechanism by which we can do that. There's no isotope buffering sort of mechanism that we are aware of. Now, mixing obviously is a way that you can mobilize old water with new water and exchange old water with new water, right? And so undeniably, part of what's going on in these systems is that nothing is separate, right? There is no, pipeline for new water to get to the stream, except the rain that falls directly in the stream. That's 1% or something in a typical landscape. the rest of it, you will have mixing with the previous water in the catchment. And that's how that older water gets mobilized. That's how it got into the stream. And that's why the young water isn't coming through to the stream, because it's been diluted by mixing, right? So I don't think your view and mine are inconsistent. I just think we're describing it in different ways.
Okay, well, we want to think about that. Since it has to do with refining that molecule or a cluster of waters.
Yes.
Some of the water that comes in mixed, so we have to because it's parts of mixed.
Of course, but the volume, but if you ask the question, what fraction of the water in the stream is that water that came in with today's rainfall, right? That question is quite straightforwardly answered by whether the stream has a tracer signature that looks like today's rainfall or not. I mean, because the only way for it not to do that is if you find a way to violate conservation of mass. Yep. Yep. Good.
Okay, if there are no more questions, let's thank our speaker.